Hello, my name is Joshua Nelson. I'm a student of Dr. Hans-Peter Schaub in the Autonomous Vehicle Systems Laboratory at the University of Colorado Boulder. Today I'm going to talk to you about my paper, The Autonomous Selection of Spacecraft Landing Location on Hazardous Small Bodies. Let's start with a quick overview of this presentation. I'm going to briefly discuss the current state of hazard detection and avoidance techniques, and an area where I see room for improvement being the use of a circular footprint for landing site selection. I'm going to propose the use of a geometrically conforming footprint and discuss how we can use the separating axis theorem to realize this idea. Then I'm going to discuss how this concept can be implemented numerically, and finally show and discuss test results on the effectiveness of this concept. Now, in the past few decades, the interest in landing on bodies such as asteroids and comets has been on the rise. An issue with this is that these bodies contain a high number of boulders, craters, and other obstacles known as hazards, as you can see here in this image taken by OSIRIS-REx of the asteroid Bennu. In response to this growing interest, there have been numerous innovations in the field of hazard detection and avoidance, particularly in the area of hazard identification. Despite some vast differences in many proposed techniques, a common similarity arises in many of them, that being the use of a circular or elliptical footprint for selection of the final landing site. While using a circular footprint is desirable because its radius can be scaled by GNC estimation errors, it is also highly restrictive of feasible landing locations, as you can see in this figure here. Now, this restriction may not present much of an issue when you have an abundance of ideal terrain to land on. However, such ideal conditions are few and far between on asteroids. With that, I am proposing what I call the geometrically conforming footprint, with the aim of fitting a more representative shape among hazards for landing site selection. This footprint naturally adds more complexity to the problem and requires much more surface information than its circular counterpart. With past research focusing on hazard identification, it is clear that the circular footprint was chosen for its simplicity and robustness. However, I believe that innovation in landing techniques has reached a point where the complexity of this geometrically conforming footprint can be allowed. The general idea is to extract some representative shapes of the surface hazards and fit a scalable 3D model of the lander among them, such that there are no intersections between the lander and the surface shapes. While this idea adds more complexity to the spacecraft landing problem, it has the potential to significantly increase the flexibility in choosing landing sites. So, let's discuss how to mathematically approach this concept, specifically using the separating axis theorem, which states that any two convex geometries do not overlap if there exists at least one axis where the projections of those geometries do not overlap. Now, note that this theorem is specific to convex geometries, and generally, spacecraft landers or hazard objects are not going to be convex. We can get around this issue by using a technique called approximate convex decomposition, which uses convex hulls to decompose non-convex geometries into a set of convex geometries. The term approximate here refers to the number of convex hulls used to subdivide a non-convex shape. The more convex hulls you use, the more accurate the union of the decomposed geometries will be to the original geometry. However, this comes at a performance cost. Further investigation of this technique is outside the scope of this paper, and thus we will continue on assuming that we have the set of decomposed convex shapes. Next, we define a surface fixed frame, S, and two convex shapes, H and K. We can use any direction in this frame to search for a separating axis. We'll label that direction beta. Further, we define two vectors for each shape. One vector from the surface origin to the centroid of that shape, and the other vector from the centroid of that shape to the closest point on that shape in the direction of beta. Then, we can say that beta is a separating axis if the distance between the two centroids in the direction of beta is greater than the sum of those RVC vectors. This inequality provides a basis for preventing the lander from intersecting any surface hazards. However, now we must discuss how to choose the direction beta. Now, every combination of convex polyhedra from the surface and the lander set must be tested for a separating axis. To determine if a separating axis does not exist, each of these combinations must be tested over a set of directions that spans the dimensions of the geometries. Of course, an obvious and minimum set of directions to test would be the basis directions of the surface frame, which we will call the coarse searching set. While any separating axis found with this set is certainly valid, you can see in the top figure here that this set has the potential of producing false negatives. Thus, to attain the sought-after level of flexibility, we will define the set of directions based off the face normal vectors of one of the polyhedra. We choose the surface polyhedron here since it is going to be fixed in the surface frame. You can see in the bottom figure that while this set has more directions, it fixes the issue of the coarse searching set. Thus, we're going to call this new set the fine searching set. Regardless of the searching set used, there will be a version of the previously defined inequality for every direction of every combination of surface and lander shapes. This leads us to how we will solve for a non-intersecting landing location. First, we set up the problem where we want to minimize the distance from the origin of some lander frame F to an objective landing location point labeled L. We can create a quadratic cost function for this problem and use the inequalities from before to create a set of constraints. Now remember that for each combination of surface and lander shapes, we only need to find one separating axis. Thus, we will introduce some Boolean decision variables into each of these inequalities, such that we may deactivate or activate each line of the inequalities. This leads to the creation of a mixed integer quadratic program with a positive semi-definite Hessian Q, a gradient C, and a set of decision variables that includes position, attitude, and Boolean variables for every one of those inequalities. The full formulation of this problem can be found within my paper. However, it is important to note here that there have not yet been constraints defined to enforce that the lander has fully touched down on the surface. Since we are currently only concerned with the effectiveness of these non-intersection constraints, this problem is only tested in 2 dimensions. Also further covered in the paper is how to obtain a solution to this problem using what's called a branch and bound technique. The important thing to know about the solutions found in this problem is they are not guaranteed to be optimal, because the feasible region is highly non-convex and there exist many local minima. The algorithm written to solve this problem is capable of searching multiple local minima. However, a maximum number of iterations has been imposed for performance reasons. This algorithm was tested on both the coarse and fine searching sets, so that the performance of each set could be compared alongside the overall performance of the algorithm itself. In these figures, you see the surface hazards colored in gray, the lander colored in blue, and the red X marking the objective landing location. Please note that the implementation of this algorithm has not yet been optimized for speed, and so raw solve time will not be in focus for the results. These objective landing locations were handpicked to stress test the algorithm. Let's start with the column on the right, which best shows the drawbacks of the coarse searching set. Here, the coarse searching set has created a boundary out of the points on the hazard closest to the objective landing location in the basis directions. Now, while the fine searching set outperforms the coarse in minimizing the distance between the lander and the objective landing location, this has come at the cost of increased search directions. Notably, in the trials on the left and the right, the coarse searching set solves 22 and 41% faster, respectively, to the fine searching set. While this was the expected outcome, the middle trial shows that the fine searching set solved 23% faster than the coarse. Not only that, but some other handpicked trials that are not shown here saw the coarse searching set get closer to the objective landing location than the fine. Furthermore, a few other handpicked trials saw no solution returned due to the algorithm hitting its max iteration limit. To understand these performance differences in a more quantitative way, a large random sampling of objective landing locations was tested. The plots on the top of this slide show the percent difference of the performance of the fine searching set relative to the coarse. And here the word offset simply refers to the distance from the lander to the objective landing location. Now these results show some pretty interesting behavior. First, it would seem that the case where the fine searching set solved faster than the coarse searching set might have been a fringe case, looking at the plot in the top left. Here we see the coarse searching set solving consistently faster than the fine searching set, however, not by significantly much on average. While this reinforces the expected behavior in terms of solve time, the next plot over shows the most interesting results. Here on the top right, we would expect to see the mean further to the right of the plot, showing the fine solution outperforming the coarse solution in terms of distance to the objective landing location. While the mean of this data is in fact to the right of the zero, the large deviation causes question to the fine's performance over the coarse. I believe this behavior is a symptom of the branch and bound searching structure that I implemented for this algorithm. However, that has yet to be investigated. Now, it is worth noting that not all 2,000 trials returned a solution. In fact, the coarse searching set only had an 85.9% success rate, where the fine searching set had a 94.3% success rate. While a 94% success rate was not the result that I had hoped to see, it does show that the fine searching set does have a clear advantage over the coarse. Putting aside these performance comparisons now, I would like to direct your attention to the bottom 2 plots on the slide, which show the actual offset from the objective landing location for each of the searching sets. Now, since the dimensions of this test were left unitless, the quality of these results is up to interpretation. However, these results show that the solution from both searching sets is within 5% of the searchable area. So now let's recap. I propose what I'm calling a geometrically conforming footprint to replace the traditional circular footprint used for landing on hazardous terrain. I claim the use of this geometrically conforming footprint can potentially greatly expand our selection of future landing sites. Then I introduced the separating axis theorem as a mathematical foundation for this concept. I have cast this concept into a mixed integer quadratic program and am solving it with a branch and bound technique. I have introduced two variations of searching sets to find separating axes between lander and hazard objects. In testing the two variations of this algorithm, I have found that the algorithm in its current state has about a 94% success rate of finding a solution. While there is plenty of room for improvement in this level of the method, I believe that this concept shows great potential going forward. Once refined, the contents of this paper will serve as a foundation in the development of a new landing guidance technique. My future plans for this concept are further covered in the paper, and I would like to thank you for listening to this presentation.